Hello everyone. In today's lecture we will talk about time division multiplexing, TDM. As we have seen earlier in this chapter, the sampling theory provides the basis for transmitting the information content of a band-limited message M of t by simply transmitting samples of this message. These samples are taken at instant 0, ts, 2ts, 3ts, and so on. In other words, these samples are taken uniformly at a rate fs, which is equal to 1 over ts. And this rate fs is slightly higher than the Nyquist rate. The Nyquist rate, which is the minimum sampling frequency, which is 2w, and we usually choose the sampling frequency fs slightly higher than the sampling rate. It's important to note that the transmission of the message samples uses or utilizes the communication channel only for a fraction of the sampling interval ts. In order to understand this, let's move to our whiteboard over here. Imagine you have a message M of t which is being sampled at instance 0, ts, 2ts, 3ts, and so on. And let's assume we're using PAM, pulse amplitude modulation, in which we take the instantaneous sample value, hold it for the duration of the rectangular pulse, let's call it capital T, and then at instant ts, we take the instantaneous sample value, hold it for the duration of the rectangular pulse, and then at instant 2ts and 3ts, and so on. So as you can see from this example, the communication channel is only used to carry data for a fraction of the sampling interval ts. That's why we are saying over here that the channel is only used only a fraction of the sampling interval ts. On a periodic basis, which means every ts we're going to be using the communication channel only for a fraction of the sampling interval. This way, some of the time interval between adjacent samples is clear for use by other independent message sources on a timeshare basis. So this statement is basically saying that we can use this clear time interval in which no data is being transmitted to transmit data from another independent messages. In order to understand this, let's look over here. Assume we have four messages, M1 of t, M2 of t, M3 of t, and M4 of t. And here I'm using different colors for different messages. Assume that the message M1 of t is sampled at instant 0, and this pulse corresponds to the first sample of M1 of t. And this red pulse over here at ts corresponds to the second sample of the message M1 of t. Now the interval between 0 and ts is only used for a fraction of the time interval ts. That's why I can sample the message M2 of t and take this pulse transmitted, and then for the next interval I can take another sample of the message M2 to transmit it, and then I can take a sample of M3 over here and M4 over here. So this way I have transmitted four independent messages during the same time interval from 0 up to ts. So it's basically sort of time share communication where the samples are taken only slightly shifted from each other. So now we can transmit other independent messages on a timeshare basis. And this is basically the idea of time division multiplexing, where we divide the time and we multiplex different independent signal on a timeshare basis. So thereby we obtain a time division multiplexing system which enables joint utilization of a common communication channel by multiple independent message sources without mutual interference, and this is basically because only one sample is being transmitted at a time, and in the next time interval another sample is being transmitted. So over here during this time interval, we're only transmitting M1, sample from M1. And during the next time interval over here, we're only transmitting sample of M2 and so on. That's why we say over here there's no mutual interference, of course, ideally. So the concept of TDM is illustrated by the following block diagram. As you can see over here, we have multiple independent messages, M1, M2 up to Mn of T. The first step is to apply some sort of anti-aliasing filter, a low-pass filter, that would limit the bandwidth of the incoming message to W. This way we can sample with sampling frequency Fs, which is slightly higher than 2W, to guarantee that there is no aliasing happening. That's why it's called anti-aliasing filter. The next step is to apply the outputs from these low-pass filters to a commutator or a multiplexer. The objective of this multiplexer is to take samples from these messages and to interleave these samples together. So it first takes a sample from M1 of T, then a sample from M2 of T, then a sample from M3 of T, until all the messages are sampled. Once this is done, it has to go back to M1 of T, M2 of T, M3 of T, and so on. As we can see over here, so it takes a sample from M1, followed by a sample from M2, M3, M4. Once done, it has to go back to M1 again, M2 again. And one complete cycle, or one frame, has to take place over the interval of TS. So it has to go back to message M1 before TS, or at exactly TS. Then these samples are applied to a pulse modulator, be it a PAM or PCM, and then send over a communication channel, and then at the receiver we have a pulse demodulator and then a decommutator or a demultiplexer. The objective of this demultiplexer is to distribute these samples back to the corresponding receivers. If this is the receiver of message 1, so the samples from M1 has to go through this reconstruction filter to the intended receiver. And then the samples from the message M2 has to go this way, samples for message M3 to go to the third receiver, and so on. And here we can understand that the commutator and the decommutator need to be perfectly synchronized in order to make sure that the samples from message M1 goes to the correct intended receiver, and so on. So, as we can see, each input message is first restricted to a certain bandwidth using the anti-aliasing filter, and the next step, the output from these low-pass filters are applied to a commutator or multiplexer, which is usually implemented using switching circuits, electronic switching circuits. And the function of this commutator is twofold, as we have said. First is to take samples from the n input messages, narrow samples, and of course sampling at a rate Fs, which is slightly higher than 2W. And the second objective is to sequentially interleave these samples together throughout the interval Ts. So message 1, sample from message M1, followed by a sample from message M2, M3. This is called interleaving. And this is basically the essence of time division multiplexing operation. So, following the commutation or the multiplexing process, the multiplexed signals applied to a pulse modulator, it can be a PAM or PCM and so on, the purpose of which is to transform these samples into a form that's suitable for transmission of the communication channel, the common channel. So it's one channel common for all the independent messages we have. So as we can see over here, the use of time division multiplexing introduces a bandwidth expansion of a factor n. How is that? Let's go to our whiteboard over here. So if during the interval from 0 up to Ts we have sample from message M1, sample from message M2, M3, and so on. So as you can see, the separation between two consecutive samples is Ts over n. If you have n messages to be interleaved together for the time duration of sampling interval Ts, so the time separation between two consecutive samples is Ts over n, which means that we have sort of equivalent sampling frequency of nfs. So fs is a sampling frequency for every message, m1, m2, m3. But overall for the TDM signal, as if we have an equivalent sampling frequency of nfs. This way we can see that we have a bandwidth expansion of n, a factor of expansion of n. So, as you can see over here, because the scheme must squeeze n samples derived from n independent messages into a time slot equal to one sampling interval Ts. So for the time duration of one sampling interval Ts, we have to squeeze n independent samples. So every sample would be basically occupying Ts over n, which results in an equivalent sampling frequency of nfs. So at the receiver end of the system, the received signal is applied to a pulse demodulator, which basically reverses the operation of the pulse modulator. The narrow samples produced at the pulse demodulator output are distributed to the appropriate low-pass reconstruction filter by using the decommutator or demultiplexer, which has to be in perfect synchronization with the multiplexer in the transmitter. This way, we can make sure that the samples of message M1 are going to the reconstruction filter and then to the intended receiver of message M1. And the samples of message M2 are going to the correct reconstruction filter to the intended receiver of message M2. This way we can make sure there is no mix-up in the samples. So synchronization is very important, it's very essential in TDM systems in order to achieve satisfactory operation. The way this synchronization is implemented depends on what kind of pulse modulation we are using. Is it PAM? Is it PCM? Is it a different type of pulse modulation? Based on the type of pulse modulation, the synchronization will be different. TDM systems are highly sensitive to dispersion happening in the communication channel. And dispersion is a phenomena that's basically attributed to the non-constant magnitude response of the channel and the nonlinear phase response of the channel. Ideally, we want the magnitude response of the channel to be flat or constant, and we want the phase response of the channel to be linear. A constant or flat magnitude response would guarantee that different frequencies are seeing the same gain or attenuation. And the linear phase would guarantee that different frequencies are seeing the same delay, because the slope of the phase response is basically the delay happening. So having a non-constant or a non-flat magnitude response simply means that different frequencies will be having different gains and attenuations, and this will cause distortion in the received message. And having a nonlinear phase means that different frequencies will be seeing different delays, and this will also result in distortion. In order to understand this, let's go to our whiteboard over here. So this is a typical frequency response of a communication channel. Ideally, we want this magnitude response to be flat, but practically it's not, which means different frequencies will be seeing different gains and attenuations. And having a nonlinear phase response would mean that different frequencies will be seeing different delays. These two combined together will result in what's called dispersion. And dispersion mainly refers to this kind of phenomena. If you are transmitting a rectangular pulse like this one, and this rectangular pulse goes through a channel with a non-flat frequency response and nonlinear phase response, the resulting or the received signal would be something like this. this red curve over here. So as you can see, the rectangular pulse is not rectangular anymore, and it kind of started to go to the next interval. It started to kind of spill out to the next interval over here, and the same for this rectangular pulse. It started to spill out to the next interval, and so on. That's why we say that TDM system is highly sensitive to dispersion, because we have rectangular pulses spaced close to each other throughout the interval TS, so any kind of dispersion will result in interference and distortion in the message. That's why we need to use an equalizer in TDM systems in order to compensate for the dispersion happening in the channel. And as we have discussed previously, we start by estimating the frequency response of the channel and then designing the equalizer to have the inverse frequency response in order to compensate for what's happening in the channel. TDM systems are more immune to nonlinearities as a source of crosstalk. By crosstalk, we mean that samples from message M1 goes to the receiver of M2, and the samples of message M2 goes to the receiver of M1. This kind of crosstalk could happen, but not due to nonlinearities in the channel. This statement has a proof, but it's out of scope. But basically, the reason for this is that different message signals are not simultaneously applied to the channel. Only samples from M1 are applied at a certain time instant, followed by sample from message M2, followed by sample from message M3. They are not simultaneously applied to the channel, only one sample at a time. In practice, it's important and necessary to limit the number of independent messages that are being sampled in one TDM frame. How is that? Because simply all the samples from all the end sources has to be squeezed together in a time interval TS. So the time allocated to every message would be TS over N, as we can see over here. So if we have N messages to be transmitted in one frame from 0 to TS, this means that the time allocated to the sample from a given message is simply TS over N. And as N capital increases, as the number of independent messages increases, this means that we will have smaller and smaller time allocated to every message, which means we have to use narrow pulses. And narrow pulses are problematic, as we're going to say in a few seconds. So, you increasing N capital, increasing the number of independent messages, would basically result in using narrow pulses, and this has many problems. First, narrow pulses are difficult to generate and difficult to transmit. And the second problem is that two narrow pulses are more affected by channel impairments, and hence reducing the system performance. So, as we have said, synchronization is a very important aspect of TDM. For a PCM system with a time division multiplexing to operate satisfactorily, it's necessary that the timing operation at the receiver follow closely the timing happening in the transmitter, of course, except for the transmission delay. Synchronization is very, very important in this case. And this requires that a local clock at the receiver need to be synchronized or to keep the time as the distant standard clock happening in the transmitter. The clock at the receiver need to be synchronized to the clock at the transmitter. One possible procedure to synchronize the transmitter and the receiver is to set aside a code element or a pulse at the end of a frame. So at the end of a frame, we can transmit a certain sequence of ones and zeros, a certain code word. And this code word can be used by the receiver in order to synchronize the two clocks. synchronize the clock at the receiver with the clock at the transmitter. So in such a case, the receiver includes a circuit. This circuit would basically search for this pattern of ones and zeros and then use it to establish synchronization between the transmitter and the receiver. One famous case study is the T1 carrier system. The T1 carrier system is used in North America in the telephony architecture used in North America. T1 system is a PCM system, so it's a pulse code modulation system, which uses TDM to carry 24 independent voice signals over the same communication channel. So in T1 system we have 24 messages that are being transmitted simultaneously over the same communication channel. So the sampling interval TS is now being divided by 24, so every message would occupy TS over 24. And as usual, we know that the human voice extends from 300 Hz to 3100 Hz, or 3.1 kilohertz. And any frequency outside this band usually does not contribute much to the quality of the voice. That's why most telephone systems assume that the maximum frequency is 3.1 K, and hence it uses an anti-aliasing filter with a cutoff frequency at 3.1 K. This means that the sampling frequency has to be slightly higher than 2 times 3.1 K, which is 6.2 K. This is the Nyquist rate, or the minimum sampling frequency, 6.2 K, and we need to use Fs slightly higher than this Nyquist rate. So typically we use sampling frequency of 8 kilohertz. 8 kilohertz will give you TS of approximately 1 to 5 microseconds. So 8 kilohertz is a standard sampling rate in telephone system. And next step, we need to use a companding. If you remember from our discussion in previous lectures, companding is basically the compression happening in the transmitter and the expanding happening in the receiver. And in North America, they use a mu low, and in the T1 systems, they use a mu low with mu equal to 255. And in order to implement the circuit that would do this mu low compression and expansion, they use like a 15 linear segments, put them together in order to approximate the mu low, as you can see over here. So we will have sort of a linear, piecewise linear characteristic where we have 15 linear segments like this one in order to approximate the mu low. And after using the compressing in the transmitter, we need to use a uniform quantizer. If you remember, using a compressing circuit followed by a uniform quantizer will give the effect of a non-uniform quantizer. So the quantizer we use over here would have a total of 255 representation levels, which means that each sample is represented by 8 binary bits, a code word that consists of 8 binary bits. So each one of the 24 voice messages that are being time division multiplexed together is represented by 8-bit word. And here they use the first bit to indicate whether this sample is positive or negative, and the remaining 7 bits to represent the value of this sample. So with a sampling rate of 8 kilohertz, the T1 system would use a TS of 125 microsecond. And this basically is the frame duration. So one frame would have the duration of 125 microsecond. And in this one frame, we need to have the samples from 24 independent voice messages. And as each sample will be converted to 8 bits. So Each frame consists of 24 code words. Each code word is 8 bits long. So the total number of bits over here would be 24 times 8, which will give you 192, plus a single bit that's added at the end of the frame for synchronization, in order to be used by the receiver to synchronize the transmitter and the receiver. Hence, the total number of bits would be 24 voice messages. Every sample is represented by 8 bits, will give you 192, plus 1 bit for synchronization will give you 193 bits. All these bits need to be transmitted for over the time duration of TS, which is 125 microseconds. And this will give you a data rate of 1.544 megabits per second. So the T1 system would have a data rate of 1.544 megabits per second, and this data rate is sufficient to transmit 24 independent voice messages sampled at a rate of 8 kilo samples per second, and each sample is represented by 8 bits per sample. This is a typical system used in North America, telephony system, and there are T2 and T3, and in general you can get the data rate for any system by following the same steps. First step, what is the maximum frequency? What is the anti-aliasing filter cutoff frequency? Based on knowing these two, you can get W, from which you can get Fs that should be larger than 2W, and then what kind of quantizer you want. How many bits per sample? Knowing the number of bits per sample, knowing the number of independent messages to be transmitted in a TDM system, and next you can get the total number of bits. And knowing TS, you can get the overall data rate.